Hi folks. Today we have with us Professor Pablo Perillo from Massachusetts Institute of Technology. He is renowned in the area of control systems in general, and he started off with a PhD from Caltech, and since then he's been in Switzerland and now back in the US for quite a while. And he's got several distinctions. Essentially, any award you can win in control area, he's won it. So it's a great honor to have him here. So let's welcome Pablo.
Great, thanks for the invitation. And I have to say, it's a pretty weird the idea of giving a talk in your office, but hopefully it will be understandable. So let me tell you what this is about. It's really about some work that I did with my student Parikshit Shah, who finished last year, and it's really about trying to understand how to do decentralized control, or what's a nice class of decentralized control problems over partially ordered sets. And I'll explain exactly what that means. I mean, that is Posets in the title. Posets stands for partially ordered sets. So kind of what's the motivation? I guess many of you are familiar with these kind of things, right? There's a lot of problems that they're decision-making problems. I'm thinking specifically in terms of controls, but there's a lot of other situations which perhaps don't fit under the umbrella of control or the classical definition of control that fit very nicely into this framework. And I'll give you a few examples of that later. But the idea is that in many problems we really have to take decisions in some decentralized way, and there's either for economic reasons or just because of physical constraints. And one of the things that I think the main idea in this work, or one of the most important things that we try to do here, is try to abstract away as much as we can for the specific formulation and really focus on the notion of flow of information. And that's, in a sense, of the goal of these languages, to try to think about what's the right mathematical language to talk about flow of information in a control system. So what's kind of the specific contributions, what I really want to tell you about is, on the one hand, our modeling language or our modeling way of thinking about this, which is in terms of partially ordered sets. And again, many of you are familiar with notions, but hopefully it will be fairly self-contained. And kind of, if you want the technical part of this work, which I think it's very interesting and it has a lot of consequences and special cases are kind of well known, but in a sense, it gives a very nice architecture for decentralized control. And kind of a technical tool in there is something called Moebius inversion, and I'll try to describe exactly what it is. And and there's some probable optimality properties. I'll tell you exactly what those are in this case. So what's the motivation? Again, there's a lot of work that people have done before in kind of the general area of decentralized control. But in particular, our starting point was a very nice work of Bulgaris, where he looked at what he called nested systems. So what's the idea in there of a nested system is that you have to, can you see my pointer? Can you actually see it?
Yes.
Yeah. So imagine here that we have two plants, P1 and P2. And what I want to do is I want to control those plants, but in a very specific way. So the way that P1 and P2 interact is that there's a unidirectional coupling between P1 and P2. So P1 is only affecting P2, but P2 does not affect P1 back, right? And what I want to do is I want to put controllers, local controllers around P1 and P2. Those are K1 and K2 in here, in such a way that they mirror the interconnection structure of the plant. So essentially, K1 is going to be collocated with P1. K1 is going to be collocated with P1. K1 is going to affect K2, and K2 is somehow also going to be local to P2. So I guess I have my two subsystems in there. They interact in a particular way, and I want the controllers to match exactly that structure. And somehow the idea is that I can abstract out, or one can abstract out what's actually happening here, just in terms of a picture like this, right? Which is kind of a flow of information that in here it's really going from P1 to P2. And there's kind of no going back in there, right? And this kind of structure is fairly natural for problems with a causal or hierarchical structure. I mean, one of the things that we're interested in, for instance, is in problems like supply chains, right? I mean, supply chains, you have exactly this kind of unidirectional or causal interaction in there.
Sorry,
Question here. So when you say 1 or 2, so you combine P1, K1 into 1 and P2, K2 into 2. Is that right?
Yeah. So in here, the way that I go from the figure in the left to the one on the right is kind of by combining, if you want, P1 and K1 and P2 and K2, and then you will have exactly this interaction. Yes. Okay. So this is an outline of what I'll talk about. Mostly, I want to tell you a little bit about the technical machinery that's in the notion of a poset on incidence algebra, which sounds complicated, but it's actually fairly easy. It's really about sparse matrices of a particular type. Then I tell you the specific control problem that we're solving and how do we solve it in state space. And then I'll tell you a little bit, perhaps the most interesting part, which is not just a solution of this problem, but what is the architecture, what's the structure of the controllers. Is that something that will generalize from our specific formulation to a much more general class of parts. So here's the definition if you want. Again, you may have seen this under a different in disguise, and you'll see why there's a number of structures that are kind of essentially isomorphic to this. But the idea of this is what's called a partially ordered set. So what's a partially ordered set? Essentially, in here, just for simplicity, I'm talking about a finite set. And the idea is I have a binary relation, which is an ordering relation between my elements. So I'll tell you the formal properties in a second. But the idea of this allows me to do is to say that one element is smaller than some other element. And there may be pairs of elements which are just not compatible, right? So that's why it's only a partial order. So mathematically, the formulation is essentially you need a binary relationship. That's kind of this binary relationship over here. And the properties that it has to satisfy is reflexivity, antisymmetry, and transitivity, right? So essentially it says that an element is less than or equal than itself. That if I have A less than B and B less than A, then A and B are the same. And also a notion of transitivity, that if A is less than B and B is less than C, then A is less than C. Right. And again, the key property in here, what distinguishes this from being a total order, is that I may have two elements and none of them is smaller than the other. Right. So just a concrete example, I think that many of you are probably familiar with. Think about the positive semi-definite matrices. And when we put the order on positive semi-definite matrices, that A minus B is positive semi-definite. Right. Or if you want non-negative vectors, it's the same thing. You can put an ordering of vectors that has exactly the same property. Right. So the idea in there is that you may have a matrix which is bigger than another one, but sometimes you might have two matrices which are incompatible. Neither of those are compatible to each other. And this kind of abstracts out if you want this property. So for everything that we want to do, I'm pretty much going to deal with finite sets. So my set is going to be finite, and we can put this kind of relations, and I'll tell you in a second what's a nice graphical relationship or graphical interpretation of this kind of partial orders. But let me define immediately next, like something that relates somehow this set type concept with algebra, with a particular algebra of matrices that we can define. And this is something called the incidence algebra of a poset. And it's something very nice. I mean, the definition, it's perhaps a little bit tricky the first time that you read it, but we'll see an example in just a second. But the idea is that these are, I can think of these as functions which are indexed by elements of the poset. So essentially think of this as a matrix, right? Rows are indexed by elements of the poset. Columns are also indexed by elements of the poset. And the idea is that they have to be 0 at certain places. They will have to be 0 whenever y is not less than or equal than x. We'll see what it means in a second. But the set of matrices or functions, if you want to think of it this way, with this property, these are called the incidence algebra. And we're going to see exactly why it's an algebra. And this is a very important notion in combinatorics. I mean, somehow it's a unified concept of a number of different things in combinatorics. I'll tell you later a few examples of this. But again, for our case, in the finite case, we can really think of these as matrices. And I'll give you examples just in the next slide. Right, so let's think about this case. So let's imagine, for instance, I have a poset in 3 elements. So these are A, B, and C. And I can give a graphical representation of this poset in terms of this directed graph. So what's my interpretation in here? So I would say that A is smaller than B, A is smaller than C, but B and C are incompatible. Right? So this is just the graphical representation of my poset, and that's exactly what's called the Hasse diagram of a poset. So if I take the definition in the previous slide, so let me just write it here. If I take this definition that says that These are square matrices. This is going to be 3 by 3. These are indexed by the elements of my poset. And the property that we will have to have is that they're 0 at certain places. Okay. So what are those places in here is when, sorry.
Could you go back last slide? So here is a set of functions. You're not talking about a single function. You said the whole set, all set of functions.
Yeah, it's a whole set of functions. Yes.
Okay.
So if you want to think about the whole set of matrices that have zeros at certain places.
All right. Okay.
Right. So in my example in here, that corresponds to the set of matrices that have zeros in there, zeros in there, zeros in there, and zeros in there. Because these correspond to the pairs of elements when the row element is not less than or equal than the column element. That was kind of what my definition was saying. Right? So for this particular example, the set of the incidence algebra is a set of matrices with this sparsity pattern. Right? Or this is what my definition, what this definition will give in this particular case. Now let me try to explain why this is an algebra. Why this is called the incidence algebra. Right? So the idea is that it's pretty obvious that when you take two matrices of this form, right? If I have two matrices of this form and you add them up, then it will have the same structure, right? I mean, you add matrices with sparsity pattern, the sum will have exactly the same sparsity pattern, right? The interesting part is, of course, what happens when you multiply them, right? And in this case, if you think about it, if you take a matrix that looks like this, and you multiply it by another matrix that looks exactly like this, then when you multiply these two, you will see that the structure of this matrix is going to be exactly the same. So again, here is that the stars represent any number, it doesn't matter what they are, and the zeros are actually zeros, right? And whenever you multiply this, let's do the easy part. For instance, when I multiply this row by this column, I get something in there. It may be non-zero. There's no reason why it should be 0. But when I multiply, for instance, this times this, I'll get a 0 in there. And this part is easy, right? I mean, these zeros in here, we kind of know where they're coming from. Because, for instance, these matrices are lower triangular, right? And we know that when you multiply lower triangular matrices, you will get something lower triangular. So somehow this is perhaps not surprising. The interesting part is that we get a 0 in there, right? And this 0 in here comes exactly because when I multiply this row times this column, the sparsity patterns are complementary, and then I get exactly a 0 over there. And somehow this is not a coincidence. I mean, this happened in this example, but it's actually a general property of every partially ordered set. Whenever it's essentially the definition of the property of a partial order, that whenever you take these matrices according to the definition that I gave, and you multiply them, if you write the definition, you will see that line out, and that the structure is preserved, right? So again, associated to any poset, there's a nice algebra of matrices, and that's going to be closed under multiplication. That's what algebra means, right? So as I said, this is true for all posets. I mean, not just for the example that I have. And pretty clear what, these properties are obvious, that it's going to be closed under multiplication by scalar. It's going to be closed under addition. If I add two elements, I'll get the same thing. And it's also closed under multiplication. That's exactly what I was proving in the previous slide, right? So this is essentially what's called an associative algebra. You get a set which is closed under addition and it's closed under multiplication. So the set of sparse matrices with a pattern that it's associated with a partial order, it will be closed under addition and multiplication. Right? And in particular also it follows as a simple corollary that if you have a matrix in this algebra and it's invertible, then the inverse is also going to be in the algebra. And that follows essentially from the Neumann series of the inverse. Right? When you write, kind of I plus A inverse, then you write it for I minus A inverse, then you have the power series identity plus A squared plus A cubed, whatever, and because all of them are in the algebra, then the whole thing is in the algebra. Right? So this is going to be very useful. I mean, these kind of things, that whenever you have some kind of algebra of this type, this is going to be closed under additions, inversions, kind of all the kind of natural operations that one may want. So what's the problem? So this is kind of a preliminary. Let me tell you the problem that we're actually solving. So the problem that we're solving is kind of, or what the typical control design problem is, which is something like this, right? So I have a plant in here. For pretty much all my discussion, I'm going to be thinking, or I'll tell you about linear systems, but a whole bunch of things that I'll say later, they will extend to a nonlinear case. But I guess I have a plant in here, and what I want to try to do is to design a controller. I'm trying to design a K in here. It has a certain properties. So what I'm going to do is I'm going to interconnect P and K. If you write it, that's kind of interconnection. And if you write it down, there's some kind of nice algebraic expression, which is just like this, which is just obtained by manipulating the matrices. There's nothing fancy here. And what we would like to do is to find the best possible K, where best, of course, depends on what criterion I'm going to use to measure that this is a good controller. And typically, one puts some kind of induced norm constraint on this transfer function. And I'll give you perhaps, and I'm actually going to consider a particular case, which I'll tell you about in a second. Right? But this is really what a control problem is about. P is given. I'm trying to find K in such a way that this interconnection has a small norm. And what makes it complicated in here is that, as you can see, this is a rational function of K. It's not affine, it's not linear, it's kind of like, there's this funny inverse in there, so it's kind of complicated, or it's, at least it's not obvious how one would solve something like this. Right?
So what's the best? I mean, you said found best K. Best in what sense?
Sorry?
Best K. What do you mean best?
Well, so typically what I will do is I want to minimize the norm of this f pk. So I will put a norm, let's say the 2 norm or the infinity norm or the L1 norm or whatever norm you want, and I'm trying to find a K that minimizes this norm. In what I'll talk about later today, we're going to put a specific norm, the L2 norm. But in the general control problem, if you want, you can put different norms depending on what you want to express.
Okay, so K is also a matrix, right?
K is a transfer function. It's a system, right? So these are not static matrices. In general, they're transfer functions, right? So what I really have in here, if you want, is a system of differential equations, and what this is representing is a transfer function of that dynamical system. And the same thing is true in here for my controller. I want K to be a transfer function. I want essentially a rational function, if you want. In mathematical terms, if you want, both P and K are rational functions of a single variable, right? Yes. So why? I mean, what's the relationship between decentralization and partial orders? Because somehow we can model in a fairly natural way the notion of decentralization, the notion of when I take an action at a particular point in time or space, then this is affecting only a subset of systems. So as an example, think again of our little system with three parts or 3 subsystems. And in this case, the transfer function that describes this, or the influence of the actions of my inputs in this subsystem, they can be associated with a matrix that has exactly the structure of the incidence algebra. So what I mean here, think about 1, 2, and 3 here as being inputs to my 3 subsystems. In here, what I have are the outputs. And the idea is if I put an input, for instance, in subsystem 1, what's going to happen is that this is going to affect all 3 subsystems, right? But if I were to put an input, for instance, only on subsystem 3, then I will only see it in subsystem 3, right? So somehow there's a direct relationship between the graph that you're writing here and the structure of this matrix. That's, in a way, it's fairly natural to model it this way. The other reason, which is perhaps more natural also, is because really what these partial orders allow us to capture is a notion of causality, right? It means that when I am affecting a subsystem at a particular point in space-time, then I can characterize the effect that that action is going to have on other points in space-time, right? And again, in here we're thinking about only in terms of space. My posets are only in space, but we can do exactly the same thing in terms of space and time, right? So it is that, again, partial orders are in general very directly related to notions of causality. And if you've ever seen anything like special relativity, if you remember your courses from physics, I mean, that's exactly what happens with the way that you model causality in terms of this partial ordering used by Lorentz cone, if you remember what happens in this case. But it's exactly the same kind of idea. I mean, we really model, if you want, the effect of an input on subsystems in terms of the structure of this matrix, and the structure of this matrix corresponds exactly to a partial order. So what's the problem that we want to solve? As I said, we're going to have a plant G is given, and it has a structure of this incidence algebra. And what we're trying to do, if you remember one of my first slides, I'm trying to write a controller, or I will write a controller that mirrors the information structure of the plan. I want it to have exactly the same structure of the plan, or in the terms that we're using, we want a controller which is also poset-causal, right? It has exactly the same causality structure. And the idea again is that this relation is, in a sense, comparing how much information one subsystem has compared to the other one, right? So it's kind of quite natural. So here's some examples, or here's a few examples, if you want, of things that fit under this relation. So I guess the first is certainly trivial. So if I have independent subsystems, then of course there's a natural, I guess there's a trivial partial order in the sense that no element is comparable to any other element. What's interesting is if you think in terms of the corresponding incidence algebra here, this is associated to diagonal matrices, right? That corresponds exactly to diagonal matrices. The other case is the case of a chain. So whenever you have a nested system, the class of systems that Bulgaris was considering at the beginning, so those correspond exactly to chains, where I can linearly order my systems in a chain, and one is affecting the next one, and like this, you know, in this monotone way, right? And if you think about the associated incidence algebra, this will correspond exactly to triangular matrices, right? When you write what algebra is associated to chains, then what you'll get is exactly the triangular matrices. And more generally, we can think of a direct acyclic graph and taking the transitive closure of this direct acyclic graph. So what that means is I will complete all the arrows. If I have an arrow from 2 to 3 and I have an arrow from 3 to 4, I would just complete it and write an arrow from 2 to 5 to 2 to 4. And if you do this for all pairs, you get a transitive closure of this graph, and that defines a partial order. And I know it's also a natural way of defining things. So the point is there's a lot of structures that somehow fit into this formulation. It's of course not fully general. I mean, there's lots of problems that don't fit under this, but somehow we want to see there's essentially a reason why we need to restrict the class of systems in some particular way. So again, let me kind of skip this. I mean, this is really about, or one of the goals that we're trying to do is to try to capture what's really essential about this kind of causal decision making. And there's a lot of variations that we can do on this basic model. So as I said before, in here we're really considering the case where my systems are, where my partial order is defined in space, but there's ways that we can define this in space and time. And also the assumption that I was using at the beginning of I want the controller structure to be exactly the same as the one in the plan, that can be relaxed. And I know it's a little more complicated, but again, we can safely ignore, I think, this for the purposes of this. There's a lot of work or related work that people have done before in the area in general of decentralized control. And let me mention perhaps the things that are more closely related to the things that we did. There's a very nice old paper of Mullans and Elliott where they look at linear systems over partially ordered time sets. So the idea in there is that you consider a linear system where time is not the usual linear chain, like the way that we think of time, but we may think about branching time or more complicated notions of time. And it's in a sense very compatible with the kind of things that we're doing. I mentioned already the work by Bulgaris. There was some very nice work of Rodriguez and Lal where they generalized some of this work and proposed this notion of quadratic invariance that kind of captures and unifies some of the class of problems of convexity appears in decentralized control. And in particular, as an offshoot, then we introduce, I guess, our poset framework in another paper, which can be understood as a special case of quadratic invariance, that you have a lot more structure that actually allows you to get a richer class of controllers. And then Swigert and Lal propose a particular solution, a state-space solution to the problem with two controllers, or two plans and two controllers. And we kind of, and what we're doing in this work is we're really generalizing, if you want, pretty much everything that happened in here. So we're generalizing this work of Swigert and Lal and connecting it to quadratic invariance. And in particular, what we want to highlight again is kind of this idea that there's a very natural architecture of controllers. And that's kind of really what I want to discuss in here. So this is the problem. So let me tell you how we solve the problem, and then I'll discuss a little bit about the architecture, about what are the architectural insights that this gives us. Right. So as I said, the problem that we want to solve is we're given P. We're trying to find a K that stabilizes this plant. We want to minimize some norm of this interconnection, and this interconnection is given by this rational form. And also we want to put structure on K. So K will have to belong to some given subspace, essentially the subspace of structural controllers, for instance, that we have zeros in the place where we wanted to have zeros. And what is difficult about this problem? Two things, right? So first of all, what's difficult is that this is a complicated rational function of K. And whenever I write this function, even though I'm minimizing the norm, this is in general a non-convex function of K. So K is constrained to live in a subspace, but what happens in here is that this function is a rational function, so there's no kind of convexity property at all that we can use. And in general, for an arbitrary subspace, it's kind of known that these kind of things are empty hard. I mean, we cannot hope to construct nice structured controllers in the general case. So what do people do, or what's kind of the standard solution, if you want, in the usual case? And by usual case, I mean whenever we don't have this kind of constraint. So imagine that I'm not doing the decentralized control synthesis, but I'm just trying to synthesize a global controller. So in that case, I don't have a subspace constraint like the one here, my second constraint. And in this case, it's known that I can reformulate this problem in a way that I will make it convex, right? And the standard trick is something like this. So remembering here, what complicates things is that this is a nasty rational function of K. So the solution, essentially, I would do a change of variables. When I call this whole term K I minus GK inverse, I would call it R, right? And then what's nice about that this gets transformed into this affine problem in R. But of course, the problem is that now, remember, I had structure on K. So if I have structure on K, then in general, the structure in R is going to be very complicated. If I take a subspace and I map it with a rational function, then I'll get a nasty algebraic variety. I will not get anything particularly nice. However, in the particular case of this incidence algebra has some closure properties, then we can translate algebraic constraints in K into algebraic constraints in R. So in particular, in the case that we were talking about in here, if G is in the incidence algebra, and I'm looking for a controller in the incidence algebra, remember I told you that products of matrices were preserved in the algebra. If I add the identity, this should also be in the algebra. If I invert the matrix, this should also be in the algebra. And if I multiply it by K, again, this should also be in the algebra. So in the case where this I has some kind of nice algebraic properties, then I can translate structure on K into structure in R. Right? There's a bijection, if you want, between properties of a controller in K and properties of a controller in R. So we can rewrite a convex constraint in K into a convex constraint in R. So at least in principle, we can solve this. Right? So what are the difficulties for this? Again, at the level that I explained, it is kind of easy. But the problem is that really I'm operating at the level of rational functions. So when I do these transformations, I'm really converting this into infinite dimensional optimization problems. I mean, they're convex, but they're infinite dimensional, right? So it's not obvious at all, certainly there's ways of approximating those ones, but it's not obvious at all that you can actually solve this efficiently in any kind of way. So what we would like to do is to get state space techniques. If I have realizations for my plan, I want to similarly produce a realization for my controller K. And perhaps more important in this, right? I mean, what I really want to get is some structure or some insight on what the controller is actually doing. I mean, somehow if I do this, the kind of things that I'm telling you is some kind of algebraic mess, right? I mean, I take this, I do these transformations, and I do this, and then at the end I get a whole bunch of numbers. But what is my controller actually doing in there? And this is really the question that we want to try to answer. Right? So let me tell you how to solve it in state space first, and then I'll tell you about the interpretation. Right? So how would we solve this in state space? So the idea is very simple. or at least in principle. Again, I'm going to use a particular norm. So what I'm going to do is I'm going to minimize the L2 norm in here. So I'm going to use that specific norm in my optimization problem. And I'm assuming that my plant is given in the traditional state space one, right? So I have matrices A, B, C, D that describe exactly what the structure of my system is. So why we're using the L2 norm? First of all, because it's very classical in control theory, right? I mean, things like linear quadratic controller, LQR, LQG, all that stuff, they very naturally use two norms. But also because there's a very important property that we're exploiting of the H2 norm, right? So think about the Frobenius norm. I mean, when you have a matrix, right, a constant matrix, and you want to compute the Frobenius norm of a matrix, right? Just the sum of the square root of the sum of the squares of the components, right? If I want to compute the Frobenius norm of a matrix, I can just compute it column by column, right? I can compute the Frobenius norm of the first column, the one of the second column, all the way to the end. And then I can write the Frobenius norm of the whole expression as just a square root of the sum of the individual norms square. And I cannot do this, for instance, for the infinity norm, for the maximum singular value norm. Right? You cannot compute the spectral norm of a matrix column by column. But I can do this for the Frobenius norm. So this separability property, in a sense, it's crucial for these kind of problems, and this is kind of what we want to see. So what's the formulation again? Imagine I have my system that's poset-causal of this form. This is the problem I'm trying to solve. I'm minimizing the two norm of this rational function. K has a structure that I want, and it has to be stabilizing. And in here, I mean, I said it earlier, but let me make it more precise. In here, we're analyzing the case where we have state feedback. So that means that my controllers at every subsystem, they actually have access to the state of each subsystem. It's not output feedback. It's really state feedback. And what that implies in particular in this case is that this term P21, it has this form. And this allows me to define a new parameter Q, which won't be just like before. So if you remember in the general case I told you earlier, I defined my parameter to be just K, I minus GT inverse. But in here I'm going to define this to include this P21 term. Right, so my parameter Q now is going to include this P21 term. What's the consequence of that? Again, that I can write this problem in the following form. I'm minimizing P11 plus P12Q. That's exactly this when I replace Q by this expression. Right, and I obtain this. And by the same argument as before, I can translate structure in K into structure of Q. Right, because all this stuff is in the algebra. So all this stuff is kind of preserved under the natural operations. Right. So now what's the idea? And perhaps, it's easy to see in an example. So remember I told you that when I compute the H2 norm, or even the Frobenius norm, if you want to think in terms of constant matrices, I know that I can write the squared norm of G just as a sum of the squared norm of the columns of G. Right. Now let's think about what that implies in terms of the problem that I'm trying to solve. Right, and I'm trying to solve something that looks like minimizing over Q, a structure Q of P1 plus P2Q. What that means, I can write this norm because I'm multiplying this only on one side. I can multiply this, I can compute this norm just as a sum of the squared norms of each one of the columns. Right? So again, think about in here, even ignore what P1 is doing. P1 is not really doing anything. But the point is when I multiply this matrix on the right, on the left by P12, what I have is a multiplication of each one of the columns by P12, and I can compute the norm of the resulting product just as a sum of the norms of each one of the columns. And what's really interesting in here is that the variables that appear in the different subproblems, that actually is joined. Right? In here, only variables of the form Q something 1 appear. Only these variables. In here, I only have these variables. And in here, I only have these variables. So I can solve this, instead of solving it as one big optimization problem, I can just solve it as separate optimization problems. And in each one of them, there's no structure. Right now, I'm solving this for a full matrix. It's not like here I have to solve for a structured matrix. In here I really have a full matrix in that. And these are problems. These subproblems are things that we know how to solve. These are essentially centralized control problems. Each one of these ones is a centralized control problems. We know how to solve this in terms of Riccati equations. There's nice formulas for solving those ones. I will not bore you and tell you what those are. But the point is, we can transform this kind of structured problem, again, for the H2 norm, into a collection of decoupled problems. Each one of those we can solve in terms of Riccati equations. So this allows us to solve for Q. We can solve for these Qs by solving all these independent subsystems. And then from this Q, we can invert this funny transformation that we were doing before. And this is what the inverse looks like. And then I can get a controller. Right. And this will actually give me, if you unravel what's happening there, you'll get explicit formulas for the controller, you will controller the rebounds. But this is important part, right? I mean, this is what we wanted to avoid. I mean, somehow in here, we don't have any insight of what actually happened, right? I started with this, I did some kind of algebraic mess, I solved Riccati equations, and at the end, we get a controller and we prove that it's optimal. But what we really want to understand, and this is what I'm going to spend my last 20 minutes on, is what is the structure of this controller, right? What is it actually doing? Can I actually understand what's happening here? Can I give a nice interpretation of what all this construction is about? Right? And this is exactly what I told you, right? If we solve this problem, essentially this solution works for all posets. It doesn't matter what poset you have, you can apply this technique. But what we really want to try to understand is what the structure. Right? So let me tell you, in order to what this suggests, or what came out of this, in a sense, is a very general architecture for decentralized controllers. And in order to explain this, I need to tell you about a couple of things. So two are fairly easy and fairly natural. It's two notions of what we call lower and upper sets and local variables. And there's just a technical part, which if you've never seen it, it's actually very interesting, which is this notion of the zeta function and the Moebius function of a poset. And there's a very important reason why they appear in a very intrinsic way in this kind of problems. And what this is going to give us is some kind of nice separation principle that will be true for this kind of decentralized control problems over posets. So what's the idea? I mean, what are these lower and upper sets? It's something very natural, right? So remember I told you that whenever I have a partial order, again, think about some kind of directly acyclic graph if you want. The point is there's a natural notion of future of everything that's going to be affected by what I do. And there's a very natural notion of past, which are all the things that affected me or that can affect me. But there's also some other elements in there that are incomparable, that I cannot affect them and they may not affect me. So what these upper and lower sets, they capture is exactly this notion. The notion of subsystems having a local future or a local past. And let me try to explain what the informal idea of the architecture is, and I'll give you the equations in a second. But the informal idea is kind of the following. So again, every subsystem in there will have this notion of local future and local past. So things in the future are the subsystems that I can affect. Things in my past are going to be all the subsystems that can affect me. And there's maybe some other ones that are incomparable. That there's no interactions between us. So it is the following. Every time that I take a decision, what I will have to do is I have to compute what the effect of my actions is going to be on everybody in my future. So if I take an action that may affect, Srinivas, I have to think about that, right? I have to simulate, if you want, in my mind, how my action is going to affect him. And not only that, I actually have to communicate to him that I'm doing this and this may affect you in this particular way. Now, what's the problem? The problem is that if I'm again in there, everybody that's in the past, it's telling me all the actions that they've taken, and they're telling me how they will affect me. And they have very different sets of information. I mean, some may know about what happened to they may have a global picture. Some may have a very local picture of what's happening. They may not know. So what I have to do now is to take into account all these predictions that people told me I have to form some kind of linear combination between those, and I have to compare those to what actually I can see in my subsystem, what my state is. Based on that comparison, I'm going to pick some kind of local control action. But then again, I cannot quite implement that local control action because I don't have a full view of what's happening. So what I will have to do is I have to integrate these local control actions with the control actions of everybody else in order to actually decide what I'm going to actually implement. It looks a little bit complicated the first time that you see it, but we're going to see how it appears in math. But the idea, again, it's very important that if I take an action, I have to think about the effect of these actions to people in the future. In here, I will receive, from the past, all the things that, the decisions that people took, trying to accommodate me. But then, they may have taken incompatible things. So I have to somehow correct that with my measurements. And then from that, I have to produce a suitable control action. So let me kind of explain, kind of how this is actually done, or exactly how this architecture works. So I said there's this notion of upper sets and lower sets, and it's kind of very simple. So idea again, this just captures, or these definitions just capture the notion of past and future, right? If I'm at a particular subsystem, let's say at subsystem 2, then this upper set is everything that's above me in the partial order. So if I'm in 2, the upper set of 2, in this case, is going to be 2 and 4. And if I'm subsystem 2, my lower set is everything that's below 2. So in this case, it's going to be 1 and 2. Again, this is fairly intuitive, right? And the formal definitions are exactly what's in here. The upper set of P is all the Q's that are above P. And the same thing is true in the other case. So this is a little bit more interesting. This is exactly this notion that I will have to keep predictions of what everybody else in the future is going to do. So in this, I have to take copies of the state. I have to carry, or the controllers will have to carry state, but they will also have to carry local copies of the state for the states that are above me, right? So if in here I'm a subsystem XY, I can split the set of states into the future, the past that I know, and the unrelated stuff. And what I'm going to do is I'm going to keep, or each subsystem is going to keep an estimate of the state of the things in the future. So for instance, subsystem 1 in here, it's going to keep around copies of the, or predictions if you want, of what states 2, 3, and 4 are doing. That's what we see in here. So subsystem 3 is going to keep a copy of what subsystem 4 is going to be doing. Same thing for subsystem 2 in here, and 4 doesn't have to worry about anything, right? So, and I can collect, if you want, all this information into a matrix in here, and by construction, this will have the structure of the poset. Right? So again, this represents, if you want, the state variables that my controller is going to have. This is a notion, and we can ignore this, is not very important, it's a notion of local products, local gains. So in here, these are just local controllers at every point in time. Again, it's just notation. This is not important. Now, this is kind of the important part, and again, if you've never seen it, this is something that's, I think, extremely beautiful, which is a notion of these set and Moebius transforms, or set and Moebius functions of a poset. So remember I told you that the incidence algebra is kind of a set of matrices, right? Giving a poset, what we have is a set of matrices with a given sparsity pattern. So there's kind of two specific elements in there, two specific matrices in there that have very nice properties. So one is called the zeta matrix of the poset. What is a zeta matrix? It's a matrix that has zeros when it should be. So remember, a sparsity pattern has zeros in certain entries. And in all the other places, I'm going to put ones. Right? It's a very, very simple matrix. I'll give you an example in a second. And the zeta and the Moebius matrix is just the inverse of that matrix. Right? So for instance, for our poset, the example that we have below, remember this was the structure of my system. This was what the matrices in the incidence algebra look like. They have this sparsity pattern, and the zeta matrix has ones everywhere except where it should have zeros. Right? So it's exactly this matrix. Now the Moebius matrix is just the inverse of this. This matrix is invertible because it's triangular and it has ones on the diagonal, and the inverse of this matrix is exactly this. Right? So again, it doesn't seem like a very interesting definition, but there's a lot of non-trivial combinatorics that are encoded in there whenever the poset has a non-trivial structure. So again, this zeta matrix is just a matrix of zeros and ones, with ones what it what zeros when it should have zeros and ones everywhere else, and mu is going to be the inverse of that. It will have in general arbitrary numbers in there, but also remember I told you that if I have something in the algebra that's invertible, the inverse will also be in the algebra, so this mu is again in the algebra. Right? Now why is that important? Because remember these are matrices whose sizes are the cardinality of the poset, right? How many elements I have. So matrices I can think of them as linear maps. Right? So what they can do is they can take a function on the poset, and I can think about multiplying this by zeta, or I can think of multiplying this by mu. Right? And by construction, of course, this is just matrix multiplication. And by construction, these are going to be inverse operations. So if I multiply by zeta, I get something. If I multiply by mu, I get something else. And this is what's called, I mean, if you ever heard about the Moebius inversion formula, this is exactly what the Moebius inversion formula is giving. So the point is, even though at this level it's just linear algebra, and it is just linear algebra, whenever you take a poset which is non-trivial, this encodes lots of very interesting combinatorics. So for instance, remember I gave you a few examples of posets, right? So one of the simplest cases is whenever my poset is a chain. So if all my elements are one after the other, right? I told you that in that case, the incidence algebra was the algebra of triangular matrices, right? So the zeta matrix in that case is going to be a triangular matrix with zeros above the diagonal and ones everywhere below. So now think about the effect of multiplying a vector times a matrix which is zeros and ones below the diagonal, and what you'll have is essentially integration. Right? What that is computing is a running integration of your vector. And if you take this matrix, again, if I had a board, I would do it, but if you have a matrix with zeros and ones below the diagonal, you take the inverse, and that's a good exercise, if you're bored or if you have a piece of paper, if you have zeros and ones below the diagonal, then the inverse of that matrix will have essentially a 1 and minus 1 in adjacent entries all along the diagonal. So the inverse of that matrix, this new matrix, is exactly going to be differentiation. So in the case where we have a linear chain, this zeta and this mu function, they're exactly doing integration and differentiation along the poset. And whenever you pick other posets with non-trivial structure, you get other combinatorial constructions. So for instance, if my poset is a lattice of subsets, there's a natural partial order between subsets, or you find that it's given by the containment relationship, then mu is essentially doing inclusion-exclusion, the inclusion-exclusion formula on posets. Or if you take, for instance, you can also define a partial order on the integers. If you take an integer to be less than or equal than another integer, if it's divisible. If I can divide one integer by another one, then I would say that this one is smaller than that. So then you can construct a matrix according exactly to what I told you, and if you compute the inverse, that's essentially a zeta function. I mean, the zeta function of the Riemann hypothesis and whatever. Right? That's exactly, if you want, what happens in this case. So the point is, there's a lot of non-trivial combinatorics. There's a lot of non-trivial statements that happen in there, and somehow they just boil down to this kind of linear algebra construction. So how do we use this in this case? Again, the key insight is that this Moebius transformation is actually local. It's a local operation that you can do with the decentralization constraints that you have. And again, as an example, think about the local chain and think about doing either integration or differentiation, right? And you can do integration or differentiation there just by message passing. And if you want to keep the running integral, what I can do is I get something from my neighbor below, I add my value, and I pass it forward. Essentially, I can do this both in the forward and the backward direction, and this will give me some kind of local operation. So both zeta and mu, they're purely local things that I can do, just as the communication constraints that I have. So what's the idea? I mean, somehow, what's the architecture of the control that we're proposing? Is essentially this. The structure of my controller is going to look like something like this. X in there is going to be, remember, this matrix that I formed with the local states and my estimates of what everybody else in the future is going to be doing. Mu in there is computing this mu transform, this Moebius transform on this set of states. Then I'm going to apply local controllers G. So these controllers G, they're acting locally in each subsystem. And then I'm going to apply zeta, which is again this global transformation that you apply, but that you can apply locally to compute what the actual control action is going to be. So again, it's exactly the structure that I was telling you before, right? So X in here, you will give the estimates of what the states of everybody else is doing. Mu in there, it's aggregating, or it's computing the differentials of what the predictions of everybody else in the past told me, and I'm going to compare it with my current state. I'm going to apply some local state G, some local controller G, and then based on these local inputs, I'm going to integrate these local inputs to actually get the inputs that I want to apply. So then it's very much like, I mean, it's not exactly this, but think about like a T inverse. I'm applying the transformation, and applying the diagonal transformation, and then applying the inverse. And what makes it very appealing, or natural in here, is that this structure, I haven't told you anything about what G is yet, other than it's local. So if you want to, perhaps let's do this first. I mean, this is kind of a graphical representation, if you want, of what the controller looks like, right? I mean, if G is my plan, then my subsystems are essentially simulating what's going to happen in the future. Then I'm locally controlling or locally computing this transformation mu by message passing on the whole graph. Then I apply my local controllers F sub I, these live in each one of my individual subsystems. And then I apply again this local passing transformation mu, message passing transformation mu, that's going to give me like my control actions. Now, what's interesting about this, again, I haven't told you what G is, what my controllers are, but what happens is that in here, these dynamics will actually decouple. If I take the closed loop equations that I had before, and I apply a suitable transformation, these equations, then what you will see is that in the new coordinates, then the dynamics actually decouple. And what that means is that I can independently design this local dynamics, G sub I, at every subsystem in a completely independent fashion. Right. So again, think about it, just if you're familiar with the observer controller type formulations, that's exactly kind of what happens in here. Whenever we implement a controller, a control system, we know that we can put a general observer, we can put an arbitrary controller, and we know that this combination is going to work. And very much this is something like this is what's happening here. And if I plug in an arbitrary G, as the only requirement that I have to make sure is that each G sub I, they stabilize a corresponding subsystem in this point. And these subsystems don't correspond, if you want, to local dynamics, and it's a little bit more complicated than that. There's these transformations that are going on before. But it's really like, kind of sandwiching, if you want, a diagonal controller between two very specific transformations, and that makes it possible for the dynamics to decouple. Right. So what's, again, in here, in what I'm describing here, there's no optimality property or anything. The only thing that I told you is if I put any G in there, I can analyze a closed loop dynamics by analyzing the individual subsystems. But in particular, the H2 controllers, the H2 optimal controllers that I told you about earlier, they will have exactly this architecture. So again, think about it exactly the way that we think about observer controller, right? I mean, there's on the one hand the notion of an observer controller that works in general, but also we know that H2 optimal controllers, they will have this interpretation in terms of the Kalman filter and kind of state feedback. And exactly the same thing is true in this case. on the one hand, we have this architecture, and on the other hand, if you want, we have an optimality result that will tell you that optimal controllers will have this architecture. There's a whole bunch of things that we can do in terms of understanding the structure of it.
Question?
Yep.
Can you go back one slide? How does, oh, I see. So, okay. I was just wondering, how is stabilization following? Okay.
Yeah, so in here, we're not claiming it. I mean, in this slide, if you want, what I'm saying is that if we plug in any G in my equations, right, then stability of this equation, so this is a form of my controller. So after I change coordinates, it will become this kind of decoupled subsystems. So then I have to pick, if I want to stabilize, I will need to pick G sub i's that stabilize each one of these subsystems. Okay. And in particular, one way of picking them is by this kind of optimal control formulation that I was telling you about earlier. But you could pick any G, or you could even change them on the fly, right? Kind of it. Okay. Okay, so this is really, I think, the main message, if you want, that I wanted to give in this talk. I mean, that there's a very natural architecture which is given, again, by this kind of, you predict states, you apply the zeta function, you apply a diagonal controller, you apply the Moebius transform, then G, then the zeta function, and then you will get a controller. And somehow in there, again, when you look at the whole thing, it's kind of complicated, everything is mixed up. But the point is, everything in here can be computed either purely locally or in terms of message passing with the architectures that we have. There's a lot of connections which I don't have time to describe, I mean, with a whole bunch of notions. So if you know in the control literature about things like Euler parameterization, I mean, that's kind of a special case of this. If you're familiar in robust optimization with something called purified outputs that people use, then that's also like a particular case of this stuff. And there's a number of things that somehow they correspond to specific choices of posets, and this is a very nice generalization of all this stuff. And there's a lot of other, as I said, if I don't want to have exactly the same structure on the controller on the plan, there's also some nice ways of dealing with those kind of issues. So that's pretty much, I think, what I want to say. I mean, the point is really that somehow when we think about decentralized control, in general, it's kind of pretty much a nightmare. I mean, there's not really a lot of structure in this problem, but when you look at sub-problems, or when we start putting a little bit more assumptions or restrictions, if you want, on the kind of structures that one may be interested, then some things may be done. And in particular, this kind of poset-like or partial orders that are quite natural whenever you have causal or hierarchical structures. And Moebius inversion and this Moebius transform seems to be the right mathematical tool to handle these problems. So there's a couple of papers in the archive, so if you want to take a look at them, I'm happy to hear your questions if you have any.